Good morning. Thanks for coming. The title of this PhD project is on seismic imaging of gas hydrate reservoir Heterogeneities. First of all, what is gas hydrate and why it's interesting? Gas hydrate is a type of class rate formed by the cage of water molecules with a gas molecule trapped inside, as you can see in this picture. If this gas molecule is methane, this gas hydrate is called methane hydrate. Gas hydrate can be formed naturally in a high pressure and low temperature environment, and that type of environment can be found at a lot of locations around the world. As you can see in this world map, the dots indicate the locations where we found or we have data indicate the occurrence of gas hydrate. Based on the publications, for example, Hitman and Dallymore's publications in 2001, it was pointed out that more than half of the organic carbon in the Earth was trapped in the form of gas hydrate. In addition, 1 cubic meters of methane hydrate can release up to 164 cubic meters of methane under standard condition. Therefore, scientists are quite interested in studying gas hydrate because it's a very promising candidate for future energy for one reason. To understand gas hydrate, a lot of questions has to be answered. For example, where are they? How much is out there? What is the concentration? If it's highly concentrated, can we produce them? And what would be the best way to produce them? So on and so forth. However, the answers to those questions are still quite limited. Starting in the 1970s, we start to have some data indicate the occurrence of gas hydrate. As you can see in this 2D seismic profile from a marine environment, it shows the ocean floor and also the bottom simulating reflector. The BSR indicate it was used as a strong indication of gas hydrate. With the limited data, it's reasonable to assume that gas hydrate is homogeneously distributed within the so-called gas hydrate stability zone. However, with more data comes in, particularly well logs, we observe that gas hydrate prefers certain locations. Therefore, the model becomes a layered model instead of a homogeneous model. More recently, a wide range seismic data in multiple well logs was available from the Malik regions, and the data indicate the well logs indicate strong lateral heterogeneities, and therefore the model becomes more patchy instead of layered. If you look at the seismic data, it also demonstrates to us that the gas hydrate encountered here can occur without showing us a BSR. So the goal of this PhD project is try to quantify or update our understanding of gas hydrate reservoir by integrating the newly available data from the Malik region located right here in this map. And we pick these locations over many other locations of gas hydrate occurrence site for many reasons. First of all, this location has been subject to a few gas hydrate research projects. Therefore, full sets of data including geology, geochemistry, geophysics, rock physics, and even production test has been done in this region. Therefore, all that makes this location the best place to do gas hydrate research. And I'll quickly show you a few samples of data that are involved in this gas hydrate in this PhD project. First of all, early acquired 2D seismic profile covers a large areas. The major boreholes penetrating through the top of the anticline. Although we know the gas hydrate, the bottom of gas hydrate stability zone is around these locations. However, we didn't observe any BSRs. Newly acquired 3D seismic data with the relevant amplitude preserved. Therefore, you can see a strong reflections at the roof of the anticline where we encountered with a high concentration of gas hydrate and weak reflections here. Sonic logs was acquired along Malik 5Ls along these boreholes. As you can see, when we have high concentration of gas hydrate, we have high velocities, and we also observed high attenuation. And I'll come back to this issue later on. 2 boreholes was drilled beside the major borehole 80 meters apart, and cross-borehole seismic survey has been done in this region, and that enables us to take a closer look at the gas hydrate reservoir. With all these data sets, I'm trying to improve the seismic imaging of gas hydrate reservoir. We know the occurrence of gas hydrate introduced significant heterogeneities. Is there a way to quantify the degree of heterogeneities? If they are, how can we use the heterogeneous model to estimate the amount of gas hydrate, and how to calibrate our models? Our model should be able to explain the phenomena we observed in the field and must not produce features we didn't observe in the field. So this presentation is organized in such a way to address those questions one by one. The occurrence of gas hydrate significantly increased both P wave and shear wave velocities. So when a seismic wave propagates through a gas hydrate bearing sediment, strong scattering and wave mode conversion will occur. Therefore, to separate P and S wave component is a better way to retrieve the elastic properties of the gas hydrate reservoir and thus improve the seismic imaging. Random media theory can be used to quantify the degree of heterogeneities due to the formation of gas hydrate, and by using a random media theory and a Monte Carlo simulation can help us to estimate the amount of gas hydrate and also the uncertainties associated with that estimation. And we can also combine a reservoir model with a finite difference software, so we can simulate seismic wave propagate through the models. The analysis of the synthetic data can help us to calibrate our model, explain at the same time explain the phenomena we observed in the field data. And in this presentation, I'll show you a numerical survey, a cross-borehole numerical seismic survey to demonstrate that point. First of all, to improve seismic imaging, a straightforward way is to improve seismic processing. Conventional seismic investigation treat P-wave energy as P-wave as the primary signal and try to eliminate the shear wave, the converted wave, the scattered energy, and also the coda wave as noise, and try to eliminate them in the processing procedures. It works in many situations. However, in the presence of gas hydrate, that processing procedure may throw out a lot of useful information, because within the gas hydrate stability zone, the occurrence of gas hydrate significantly increased the P wave and the shear wave velocities, more than 50% for P and 80% for S wave. So when a seismic propagates through this region with strong contrast, strong scattering in a wave mode, the conversion will occur, and I'll demonstrate that using this simple model. It's a simple toy model actually. It's simple because it's layered everywhere except at the locations of gas hydrate. I put 3 blocks here to mimic the occurrence of gas hydrate. Shear wave component and P wave component. As you can see, when a wave propagates through P wave front propagate through the 3 blocks, you can see strong P to P scattering and also P to S converted energy, because that's the wave front of shear wave. And when the shear wave propagates through, you can see a strong shear wave to shear wave converted energy, and scattering, and a shear wave to P wave converted energy. And this is just a snapshot I showed you before. So that's the motivation to separate P and S wave. To do that in theory is quite simple. It can be calculated. P wave component and shear wave component can be calculated using this equation. You may notice that we need 3 components, and we also need to do a spatial derivative. 3 component is easy to get. In the field, to do the spatial derivative is not that easy. We need to invoke a few approximations, approximations. So to do a spatial derivative at this location, we need to know the wave field around it. So to do the vertical derivative, we can use the receivers on the top and receivers at the bottom to approximate a vertical derivative. However, we don't have receivers beside. Therefore, instead of shifting the receivers within the Earth, which is not possible, we shift the source on the surface. So use the wave generated by the shifted source here, received by the receivers along the borehole, to approximate the wave field generated by the original source and received by our virtual receivers here, so that we can approximate a spatial derivative. In the field, we have a multiple offset VSP data available in the Malik regions. That's the receiver boreholes and a few shot on the surface. So we can test these algorithms in the field data. Apply these algorithms to the synthetic data. This is horizontal and vertical component of VSP data. Both of them have downgoing P and shear wave energy, and also converted the P to S and S to P wave converted energy. I've applied this separation algorithms. You can see in the shear wave component, you hardly see any downgoing P wave, and most of the energy here are related to the shear wave and also P to shear converted shear wave energies. In the P wave component, you observe a strong downgoing P wave, and you still have some leftover shear wave energy, because this is second order approximations. You can compare that with the ideally separate the P and S wave component. This algorithm works really nice. It even works in the presence of noise. You may know that from my thesis, I did apply these algorithms to the multiple offset VSP data and also the 9 component Weyburn field data, field VSP data. No satisfactory result has been outputted yet, because none of this VSP data was acquired with this extra criterions in mind. Therefore, to first test this algorithm, we do need the field data was acquired with this extra but critical criterions in mind. So next thing I show you something that works. Random media theory was widely used to describe heterogeneous materials or complex media. It can also be used to describe or quantify the degree of heterogeneities due to the formation of gas hydrate. The first thing we need to do, we need to pick what type of random media we're going to use. According to Holliger, if you take a sonic locks or well locks, no matter what type of lithology it penetrates through, if you take whole locks and for example, the Malik 2L38 penetrate through permafrost sediments and gas hydrate bearing sediments. You take the whole well locks, calculate the Fourier transform, and calculate the power spectrum as a function of wave number, 1 over wave number. If you see a strong linear decay or a power law feature, according to Holliger, that's a strong indication of the self-similar properties of the material. And one of the best candidates to describe a self-similar media is the so-called von Karman type random media. Here I show you a few examples of von Karman type random medias approaching to a power law when the wave number is larger than a certain amount. I'll use these pictures to give you a physical meaning of this, what this A and Hertz number nu is doing. And in a horizontal direction, the correlation length is increasing, and in the vertical direction, the Hertz number is increasing. So for the same correlation length, if you increase the Hertz number, you can see the model becomes more and more smooth. Therefore, the Hertz number is controlling the richness of small-scale heterogeneities. For the same Hertz number, if you increase the correlation length from 10 meters to about 100 meters, the scales of the models increase. It approach to a layered model, as you can see here. So the correlation length actually is controlled. The average scale of heterogeneities, and with these parameters we get ready to generate our random media, our heterogeneous gas hydrate reservoirs. And one important application is to combine that with a rock physics model to estimate the amount of gas hydrate. The rock physics model we use is the modified Biot-Gasman theory, described by these equations here. In the left corner is a pictorial representation of this equation. It simply establishes the relationship between the formation velocity ratio, the density, and the gas hydrate concentration. As long as we know two of them, we can derive the other one. From the previous modeling algorithms, we can calculate a cube of density and a cube of velocity ratio. Two of them used as input. I can get the other one, which is the gas hydrate concentration cube. And after that, I can count pixels by pixels and sum all the values up. I get one number, and that is the volume content of gas hydrate within a unit rock volume. However, to generate models like this, we need both vertical correlation lengths and also the horizontal correlation lengths. But we don't have well locks drilled along a horizontal direction, therefore AX and AY is not available. The right panel shows you actually is the volume content of gas hydrate as a function of horizontal correlation length. As the correlation length decrease from 800 meters down to about 100 meters, the volume content of gas hydrate decreased from 2.6% down to 1.5%. So the point here, I have a few examples here, is to we do need some external information to decide what is the correlation length here, so that we can pinpoint the amount of gas hydrate in the Malik regions. The second application is to combine that with a finite difference program, so that I can simulate wave propagation through the gas hydrate reservoir. And by analyzing the synthetic data, we're able to explain the phenomena we observed in the field, and at the same time we can calibrate our random medias, calibrate our heterogeneous model. And with this model, we can do a surface reflection survey, we can do a VSP survey, we can also do a cross-borehole seismic survey. And in this presentation, I will use a cross-borehole numerical survey as an example to demonstrate how I use the synthetic data to explain the high velocity and high attenuation I just mentioned at the very beginning of this presentation, and at the same time how I can use that to calibrate our heterogeneous model. So here is the acquisition geometry. Two boreholes 80 meters apart, same as the field. Source along this borehole, receivers can be along this boreholes. AX equals 10, pseudo locks to show beside, source in time domain, source in the frequency domain. And to quantify the attenuation that occurs within a model, I take advantage of this modeling. I put receiver arrays along this locations where we have relatively coherent large-scale gas hydrate concentration zone, and the second receiver arrays is within a low velocity zone where we don't have gas hydrate. and then I can put every single grid along the receivers here, source here as a point source, so that I can simulate a plane wave from the propagate from left to the right. As you can see, the wave propagate from the source boreholes to the receiver boreholes. You can see when there's a high velocities around these locations, energy propagate much faster as we expected, and also the energies decays much faster compared to the energies in the slow formations, because the energy scattered or refracted into the low velocity zones. So to quantify the attenuations, I use the spectral ratio method. What I do is I use a small windows to pick the first arrival, transfer the first arrival energy from time domain to frequency domain. You can take a look at the frequency content of the first arrival. The color is the logarithm of the amplitude. The frequency is not coherent because scattering occurred. Now we need to pick a frequency have coherent amplitude here, and we pick this one, and frequency at this location is about 750 Hertz. And just remind you, it's just the major energies if you look at the source spectrum. Now I pick the amplitude along this line and fit the logarithm of the amplitude ratio with the arrival time differences. The slope is related to Q values. By fitting that, I can calculate Q values equals to 19. I can do the same thing for region 2, but it's not that quiet. It's quite noisy because the energy is scattered into this region and make this way more difficult to estimate the Q values. But we can still do that. Transfer the first arrival to frequency domain, fitting the logarithms. We get the Q value equals to 80. If you look at the field data that observe the strong attenuations, their VSP data, sonic logs in the cross borehole, seismic data, they all observe high attenuation and high velocities, and all of them indicate a Q value, apparent Q value between 5 and 20. In the previous numerical survey on the heterogeneous gas hydrate reservoir but pure elastic model produced the same level of Q values as we observed in the field. Therefore, and also the example in the VSP of VSP data in the thesis also confirms that the high velocity and high attenuation can be attributed to the heterogeneous distribution of gas hydrate in the region. And one byproduct of this cross-borehole numerical survey is its link one of the parameters, the model parameters, to the measure the Q values. Therefore, you can use the measure the Q values to say something about our horizontal correlation length of the model. So that's one way to calibrate our model. So all these previous studies focus on the roof of the anticline structures here, because we have the boreholes was drilled at this location and we encountered a high concentration of gas hydrate. So this region received the most attention in this PhD project. But modeling results can also help us to explain the occurrence of gas hydrate in the large areas by combining with the local geology here. The top is the base of the permafrost. The temperatures below that increase to higher than 0 degree. Two anticline structures cross the top and bottom of the gas hydrate stability zone. This is a reference anticline structures here. And with a deep source that was in production, the natural source, they migrate all the way up, and because of the track mechanisms at the roof of the anticline, the gas was formed, the gas hydrate in this location. Therefore, we observed the strong concentration of gas hydrate. What about outside of the anticline structure, but still within the gas hydrate stability zone? Because there's a fluid pathway, the fluid pass through the gas hydrate stability zone and reaches to the surface. For example, therefore, we observe the mud volcanoes or the bubbles on the surface. This is because the fluid, the gas saturated fluid, migrate all the way up through the fluid pathway. Well, therefore, I can say in this situation, the winner is geology. It's not just the pressure and temperature controls the gas hydrate stability and also gas hydrate distribution. You also have to take into the local geologies into account. So this is a comprehensive pictures. It's an update from the previous cartoon. It's moved from cartoons to relatively quantified regions. This region get intensively quantified because we have the most data here, and move away from the trap mechanisms. There's a fluid pathway, so the concentration in this location is much slow. You can also explain this. You can also look at these scenarios from the distribution of velocities here. In Malik 5L, we have gas hydrate concentrations, most of them distributed within this region, so we definitely see a second bump as you move further away from the trap mechanism. You probably see less and less bump till you observe, for example, 12 kilometers away from this borehole, you observe the currents of gas hydrate may just contribute to heavy tails in this location. So I'm ready to draw the conclusions here. To separate P and S wave mode is a better way to retrieve the elastic properties and thus improve the seismic imaging of gas hydrate. Random media theory can be used to quantify the degree of heterogeneities, and by using multicolor simulation we can quantify the estimations of the gas hydrate amount. By combining the random media, randomly heterogeneous gas hydrate reservoir with a finite difference software, we can use the synthetic data to explain some phenomena. For example, the heterogeneous distribution of irregularly shaped high velocity regions contribute to the high velocity and high attenuation phenomena. And we can use a cross-borehole seismic survey to calibrate our models, but also offset VSP can also be used to do the same job, but I prefer the cross-borehole seismic survey because they have the highest resolution. So if you accept the only thing for certain is uncertainty, then what can be done in the future is just to keep updating the uncertainties. I'll show you one example. Here is a borehole, heterogeneous borehole, randomly generated. They honors the statistic properties we observed in the borehole logs, and also in addition along these locations the model exactly matches the well logs. So it's not a pure random model, it's a model conditioned by a well logs. It can do the same thing for two boreholes, and the models along this borehole locations matches the measurement in the field. So one observation I made is by integrating boreholes, the uncertainties actually can decrease. Therefore, I can predict with more and more data, soft constraint, hard constraint, can further update these models by integrating more and more available data. I also look forward to apply this idea, this model, to a different environment like marine situations. I can use this model to explain bullseye events, as I show you here. As I show you, this is a small small simple model, but you can compare the synthetic data with the field data. This model also explained that the frequency-dependent seismic blanking can be explained by the heterogeneous distribution of gas hydrate. Thank you.